Chapter 17 Monitoring and Record Keeping. Welcome to the comprehensive audio study guide for Chapter 17 Monitoring and Record Keeping. This chapter is widely considered the legal and ethical backbone of the sterile processing profession. While we often focus on the physical mechanics of cleaning and sterilization, this chapter focuses on the data that proves those processes were successful. We will navigate this chapter by following the flow of the department, beginning with the introduction and the fundamental importance of documentation, and then moving into the specific monitoring requirements for the decontamination area. Introduction. You must understand the concept of the invisible goal in our profession. Sterility cannot be seen with the naked eye. If you hold two instrument packages in your hands, one that has been perfectly sterilized and one that has never entered an autoclave, they look exactly identical. There is no glowing aura around a sterile instrument. Because we cannot see sterility, we must rely entirely on data to verify that the conditions for sterilization were met. This brings us to the golden rule of sterile processing, which serves as the foundation for this entire chapter. If it is not documented, it did not happen. You could have performed a task perfectly, but without the record to prove it, legally and functionally, it never occurred. The importance of accurate records. Sterilization records are not merely administrative paperwork. They are critical legal documents that serve two primary purposes. First, they protect the patient by ensuring traceability. If a patient acquires a surgical site infection, the facility must be able to trace the instruments used on that patient back to the specific load and cycle to prove they were sterile. Second, they protect the facility by providing proof of compliance with standards and regulations. A critical logistical component of record keeping is the retention policy. The question often arises regarding how long a facility must keep these records. The standard rule is that records must be maintained for a specific time period determined by local and state regulations or the facility risk management and legal departments. While this varies by geographic location, a common requirement you will encounter is a retention period of 7 years or more. General monitoring. There is a common misconception that monitoring only occurs on the clean side of the department at the sterilizers. This is false. Monitoring is a comprehensive activity that occurs in all areas of the department, starting from the moment items enter the decontamination area. Effective monitoring requires a combination of mechanical, chemical, and biological verification methods to ensure every piece of equipment and every process is functioning within established parameters. Decontamination area monitoring. The decontamination area is the first line of defense against infection, and its processes must be monitored rigorously. We break this down into 3 distinct categories, which are water quality, automatic DOS units, and mechanical cleaning equipment. First, we must monitor water quality. Water is the primary vehicle for cleaning, but it can also be a source of damage if not monitored. Technicians must regularly test for hardness, pH levels, and chloride content. This is critical because poor water quality, specifically water that is too hard or has high chloride content, will damage instruments. This damage often manifests as pitting and corrosion, which creates microscopic hiding places for bacteria and eventually leads to total instrument failure. Second, we verify automatic DOS units. Modern decontamination sinks and automated washers often utilize pumps to automatically dispense detergent and enzymatic cleaners. We cannot simply assume these pumps are working. Technicians must verify that the pumps are delivering the correct volume of chemicals. If the pump delivers too little detergent, the instruments will not be clean. If it delivers too much, it can leave toxic residuals on the devices or cause excessive foaming that impedes the wash action. Third, we monitor mechanical cleaning equipment. This includes your washer disinfectors and ultrasonic cleaners. We cannot trust that a washer is working simply because the lights are on. We must prove it. For automated washers, we use daily verification tests, often referred to as commercially available soil load tests or TOSI tests. These tests verify the mechanical cleaning efficiency, specifically the impingement pressure and spray arm rotation, as well as the effectiveness of the enzymatic chemistries. For ultrasonic cleaners, we must test the sonic energy. The standard method involves a foil test or specific cavitation wafers. When a piece of aluminum foil is submerged in the ultrasonic bath, the cavitation energy should create a uniform pattern of small pinholes or pitting on the foil. If the foil comes out smooth, it indicates that the transducers are not functioning, and the machine is not actively cleaning the instruments. Having established the rigorous protocols for mechanical cleaning validation in the decontamination area, we now shift our focus to the monitoring of chemical disinfection processes. This section specifically addresses high-level disinfection, or HLD, which is primarily used for semi-critical devices such as flexible endoscopes. Because these devices are processed using potent chemicals like glutaraldehyde or orthothialdehyde, also known as OPA, the margin for error is non-existent, and the monitoring requirements are extremely strict. High-level disinfection monitoring. The monitoring of high-level disinfection is centered on verifying the potency of the chemical solution. Unlike steam sterilization, where we measure physical parameters like pressure, chemical disinfection relies heavily on the concentration of the active ingredient. This brings us to the critical concept of the minimum effective concentration, or MEC. Over time, and as wet instruments are introduced into the solution, the chemical becomes diluted and loses its ability to kill microorganisms. To ensure the chemical remains strong enough to achieve high-level disinfection, we utilize a chemical-specific test strip. The frequency of this testing is a common subject for exam questions and a vital component of daily practice. The rule is absolute. You must test the high-level disinfection solution with a test strip before each use. While some older guidelines or facility policies might suggest daily testing, the industry best practice and the standard you must adhere to is testing before every single cycle or manual soak. This ensures that the solution has not fallen below the minimum effective concentration since the last time it was used. There is a strict protocol for handling test failures. If the test strip does not change color to indicate the chemical is potent, the solution represents a failure. The technician must discard the solution immediately. This rule applies regardless of the expiration date on the bottle. A shelf life date, such as 14 days or 28 days, is merely a maximum limit. It does not guarantee potency. Only the daily and per-use test strip can verify that the chemistry is active. If the solution fails the strip test on day 3 of a 14-day cycle, it must be poured down the drain and replaced. Manual disinfection monitoring. When performing manual disinfection, the technician is responsible for creating the data record that an automated machine would otherwise generate. Documentation for manual soaking is labor-intensive but legally required. For every single device processed, the logbook must contain specific data points. First, you must record the results of the MEC test strip to prove the chemical was active. Second, you must document the temperature of the solution. The chemical only works effectively at a specific temperature defined by the manufacturer, and this must be measured and written down. Third, you must record the time. The device must be submerged for the exact duration required by the instructions for use. Finally, to ensure patient safety and traceability, the log must link the specific scope serial number to the patient on whom it will be used. Automated endoscope reprocessor monitoring. Most facilities now utilize automated endoscope reprocessors, or AERs, to standardize this process. However, automation does not remove the need for monitoring. For AERs, the monitoring process is twofold. First, we still verify the chemical potency. Even inside a machine, the chemical degrades, and the technician must often manually test the MEC of the reservoir before running the machine. Second, we monitor the cycle parameters through the machine printout. Much like a steam sterilizer, an AER produces a printout at the end of the cycle detailing the exposure time, temperature, and successful completion of each phase. The technician must review this printout to verify that no error codes occurred and that the cycle met all parameters. Once verified, this printout is signed and stored as a permanent legal record. This document proves that the flexible endoscope was disinfected according to standards before it was returned to patient use. Sterilization area monitoring. Moving from the disinfection of semi-critical devices, we now enter the critical domain of the sterilization area. According to AAMI ST 79, which is the gold standard for steam sterilization, we rely on three distinct but interconnected types of monitoring to ensure patient safety. These are physical monitoring, chemical monitoring, and biological monitoring. You cannot rely on just one method. You need all three to verify that the conditions for sterilization were met and that the process was effective. Physical monitoring. The first pillar of this system is physical monitoring. This refers to the real-time data provided by the sterilizer itself during the cycle. This includes the charts, analog gauges, and digital printouts that record the critical parameters of time, temperature, and pressure. This data tells you that the machine functioned mechanically. It confirms that the chamber reached the correct temperature, held it for the correct exposure time, and achieved the necessary pressure levels. However, there is a vital limitation you must understand. Physical monitoring does not prove sterilization. It only proves that the machine ran the cycle parameters. Just because the printout says 270 degrees does not mean the steam actually penetrated the center of your instrument trays. Despite this, physical monitoring carries a critical operator responsibility. At the end of every single cycle, the operator must physically retrieve and review the digital printout to verify that all parameters were met. Once verified, the operator must initial the printout. This signature is a legal attestation that you checked the cycle before releasing the load. If the printout is missing, or if it shows a failure, such as a temperature drop during the exposure phase, the load must be immediately quarantined and cannot be released. Chemical indicators. The second pillar is chemical indicators, or CIs. These are devices that use sensitive chemicals to change color or form when exposed to specific sterilization parameters, such as heat, time, or the presence of steam. We classify these indicators into distinct types according to ISO 111401, and understanding these types is essential for your daily work and the certification exam. Type 1 process indicators are external indicators, most commonly seen as the autoclave tape placed on the outside of a wrapped package. The purpose of a Type 1 indicator is purely logistical. It distinguishes processed items from unprocessed items. If you see the black stripes on the tape, it simply confirms that the pack was inside the machine. It does not prove the pack is sterile, nor does it prove that parameters were met. Type 2 specific test indicators are used for specific equipment tests. The most famous example is the Bowie-Dick test. This indicator is used exclusively in dynamic air removal sterilizers, also known as pre-vacuum sterilizers, to test for air leaks and verify the efficiency of the air removal system. It does not test for sterilization lethality. It tests the mechanical ability of the vacuum pump to remove air. Type 5 integrating indicators are the most robust and commonly used internal indicators. A Type 5 integrator reacts to all critical variables of the sterilization process, time, temperature, and the presence of steam. They are designed to parallel the performance of a biological indicator, offering a high degree of confidence. Because of their accuracy, some facilities use Type 5 integrators to release non-implant loads. Type 6 emulating indicators are cycle-specific devices. A Type 6 indicator is engineered to verify a precise cycle, such as 4 minutes at 270 degrees Fahrenheit. If you run a different cycle, this indicator will not yield an accurate result. Finally, we must address the internal chemical indicator rule. An internal CI must be placed inside every single package, peel pouch, or rigid container processed in the department. The placement is not random. The indicator must be placed in the geometric center or the most challenged area of the pack. We place it in the hardest spot for steam to reach to prove that the sterilant successfully penetrated the entire package and reached the instruments inside. Biological monitoring. Having secured the process with physical data and chemical verification, we now arrive at the third and final pillar of sterilization monitoring, which is arguably the most critical. This is biological monitoring. While physical gauges tell us the machine got hot, and chemical indicators tell us the steam entered the pack, neither of these methods can guarantee that microorganisms were actually destroyed. To prove lethality, we must use biological indicators, or BIs. A biological indicator is a device that contains a known population of highly resistant bacterial spores. We use spores because they are the most difficult life form to kill. If the sterilization process can kill these resistant spores, we can be confident that it also killed the less resistant bacteria, viruses, and fungi on your surgical instruments. This is why the BI is considered the gold standard of sterilization assurance. It is the only test that proves lethality. For your exam and daily practice, you are required to memorize the specific names of the spores used for different sterilization methods. You cannot mix these up. The first spore is Geobacillus stereothermophilus. This spore is highly resistant to heat and is used for steam sterilization, ozone sterilization, and hydrogen peroxide gas plasma sterilization. A helpful mnemonic device to remember this is to associate the word steam with stero. If the method involves steam or vaporized hydrogen peroxide, you must use Geobacillus stereothermophilus. The second spore is Bacillus atrophius. This spore is used for ethylene oxide, also known as ETO, and dry heat sterilization. It is critical that you distinguish between these two organisms. Using the wrong spore test for a cycle renders the test invalid. This leads us to the question of frequency. How often must we run a biological indicator? According to the AAMI ST79 standard, the minimum requirement for steam sterilization is that a BI must be run at least weekly. However, AAMI strongly prefers and recommends that a BI be run daily, or specifically, on every day that the sterilizer is in use. There is one major exception to this rule where the schedule is not optional. Every single load containing an implantable device must be monitored with a biological indicator. You cannot skip this step for implants. Process challenge devices. To run a biological test, we do not simply throw the vial into the chamber. We must place it inside a process challenge device, or PCD. In the past, these were commonly referred to as test packs. A PCD is a device designed to present a challenge to the sterilization process that is equal to or greater than the challenge posed by the most difficult item in the load to sterilize. Ideally, the PCD is the hardest thing in the machine to penetrate. If we can kill the spores inside the PCD, we can assume we killed the microorganisms on the instruments. A typical PCD contains the biological indicator vial and a Type 5 chemical integrator. These are placed inside a challenge system, which might be a stack of surgical towels or a commercially manufactured challenge pack that restricts air removal and steam penetration. Location is also critical. In a steam sterilizer, you cannot place the PCD just anywhere. It must be placed in the area of the chamber that is most difficult to sterilize. Because air is heavier than steam, it falls to the bottom of the chamber, making the area directly over the drain the coldest point and the location most likely to trap air. Therefore, you must place the PCD flat, directly over the drain line. This ensures that we are testing the worst-case scenario in the machine. Implants and load release. With the fundamental understanding of biological indicators and process challenge devices established, we must now apply these tools to the strictest protocols in the department. The most critical of these rules concerns the processing of implants. An implant is defined as any device placed into a surgically or naturally formed cavity of the human body that is intended to remain there for a period of 30 days or more. Because these devices are left inside the patient, the risk of infection is significantly higher, and the consequences are more severe. The implant rule is non-negotiable. Any load containing an implantable device, such as screws, plates, or total joint replacements, should be monitored with a process challenge device containing a biological indicator and a Class 5 integrator. The standard procedure for these loads is quarantine. You should not release an implant load for use until you have the final result of the biological indicator. This means the load sits on a cart, untouched, until the incubator gives you a negative result, proving the spores are dead. However, in trauma situations, emergency release may be necessary. If an implant must be released before the BI result is known, you must follow strict documentation protocols. You are required to complete a premature release form. This document must list the patient name, the surgeon name, and the specific procedure. This ensures immediate traceability. If the biological indicator reads positive later that day, the facility needs to know exactly which patient received the device so the surgeon can be notified immediately to treat the patient for potential infection. Validation and verification. Before we discuss specific machine protocols, we must clarify two terms that are frequently confused: validation and verification. Validation is a process performed by the manufacturer. The company that built the sterilizer performs rigorous scientific testing in a lab to prove that the device is capable of sterilizing instruments. They validate the science. Verification is performed by you, the facility. We perform verification to confirm that the equipment is working correctly in our specific environment, with our specific water and steam supply. Sterilizer-specific monitoring protocols. The tests you run depend on the type of machine you are using. Furthermore, if your sterilizer runs multiple types of cycles, such as a gravity cycle and a pre-vacuum cycle, you must perform multiple cycle testing. You cannot test just one. Each cycle type used must be verified independently. For dynamic air removal sterilizers, also known as pre-vacuum sterilizers, we have two requirements. Because these machines use a vacuum pump to remove air, we must test that vacuum daily. You must run a Bowie-Dick test, which is a type 2 chemical indicator, in an empty chamber at the beginning of each day. In addition to this, you must run a biological indicator test pack at least weekly, though preferably daily. For gravity displacement sterilizers, the protocol is different. These machines do not use a vacuum system, so there is no need to run a Bowie-Dick test. However, you must still run a biological indicator test pack at least weekly, preferably daily. For immediate use steam sterilization, or IUSS, the cycles are high speed and critical. Therefore, the standard requires a daily biological indicator test for each cycle type used. For tabletop sterilizers, which are often found in clinics, the equipment is prone to user error and mechanical drift. Therefore, a daily biological indicator is highly recommended to ensure patient safety. We must also mention ethylene oxide and hydrogen peroxide sterilizers. The standards here are even stricter. For ethylene oxide, the standard requires a biological indicator in every single load. You cannot run a load without a BI. For hydrogen peroxide, best practice recommends a daily BI, or preferably every load monitoring, depending on the specific manufacturer's instructions. The control BI. Finally, we must discuss the control BI. You cannot simply run a test BI, you must also run a control. The control BI is a biological indicator from the exact same lot number as your test BI, but it is not sterilized. You take it straight from the box, crush it to activate the growth media, and place it in the incubator. The purpose of the control is to validate the test itself. We need to verify two things. First, that the spores were actually alive and viable to begin with. Second, that the incubator is heating up and working correctly. The logic for interpreting results is critical for your exam. The test BI, which went through the sterilizer, should be negative, meaning no color change and no growth. The control BI, which stayed on the counter, should be positive, meaning the liquid changes color and the spores grow. If your control BI reads negative, the entire test is invalid because it suggests the spores were dead before you even started. You must discard the pack and start over with a new lot number. Sterilization failure and recall protocols. Having reviewed the strict protocols for implants and the necessity of control BIs, we must now address the worst-case scenario in the sterile processing department. What happens when the monitoring system fails? This final section covers the critical protocols for sterilization failures, the logistics of lot control, and the requirements for staff competency. A sterilization failure is indicated by a positive biological indicator. If your test vial shows bacterial growth, it is a red alert for the entire department. The immediate action is mandatory. You must initiate a recall. However, for the exam and for risk management, you must understand the scope of this recall. You cannot simply recall the single load that failed. You must recall every single load processed since the last known negative biological indicator. Here is the logic you must understand. If you ran a successful BI on Monday morning and a failed BI on Tuesday morning, you know the machine was working on Monday, and you know it failed on Tuesday. However, you do not know exactly when it broke. It could have failed 5 minutes after the Monday test. Therefore, every load processed in that window is suspect. All items processed between Monday's test and Tuesday's test must be retrieved, unwrapped, and reprocessed. Before assuming the sterilizer is broken, however, you must perform troubleshooting. Experience shows that many failures are actually operator error. You must investigate whether the technician selected the correct cycle for the load, whether the PCD was placed correctly over the drain, or if the cart was overloaded, preventing steam circulation. Only after ruling out human error do we attribute the failure to the machine. Lot control numbers and dating. To facilitate these recalls, every sterile package must carry a precise identification label, often called the license plate of the package. This is the lot control number. A valid lot label must contain 3 mandatory components. First, the sterilizer ID, which tells us exactly which machine processed the item. Second, the cycle number, which tells us which specific load the item was in. Third, the date of sterilization. Regarding the date, many facilities utilize the Julian date system. This is a continuous dating system that numbers the days of the year from 001 to 365. Instead of writing January 1st, we write 001. Instead of January 31st, we write 031. February 1st becomes 032. You must be comfortable reading these numbers. If you see a lot number ending in 032, you know instantly that the item was sterilized on the first day of February. This system simplifies the math when calculating expiration or rotation schedules. Staff education and competency. Finally, we must recognize that monitoring the machines is only half the battle. We must also monitor the people. Staff education and competency are legal requirements. Staff must be trained upon hire and assessed annually thereafter. Additionally, continuing education credits are often required to maintain certification and keep skills current. Documentation is key. A competency is not merely a written test. It must include a documented observation of specific tasks. A supervisor must physically watch you perform a critical task, such as a Bowie-Dick test or loading a sterilizer, and sign a document stating that the technician successfully performed the task according to standards. If the observation is not documented, the technician is not deemed competent. Conclusion. In conclusion, Chapter 17 teaches us that monitoring is the conscience of the sterile processing department. Without biological indicators, chemical indicators, and physical printouts, we are merely cooking instruments, not sterilizing them. We can wash them, wrap them, and heat them up, but without the data to prove lethality, we are gambling with patient lives. The integrity of the entire hospital system rests on the accuracy of the records you keep and the diligence of your monitoring. This concludes our comprehensive study of Chapter 17 Monitoring and Record Keeping. Rapid-fire review. Although we have concluded the main narrative of Chapter 17, the density of technical data in this chapter requires a dedicated review session. To ensure you are fully prepared for the certification exam, we will now conduct a rapid-fire review of the critical terms, numbers, and rules we have covered. Consider this your final checklist for mastery. Critical spore recognition. You must immediately recognize the correct biological indicator spore for each sterilization method. If the exam asks for the spore used in steam, ozone, or hydrogen peroxide sterilization, the answer is Geobacillus stereothermophilus. Remember the link between steam and stero. Conversely, if the exam asks for the spore used in ethylene oxide or dry heat sterilization, the answer is Bacillus atrophius. Mixing these two up is a guaranteed way to fail a question. Monitoring frequencies. Next, we review the mandatory frequencies for testing. For high-level disinfection test strips, the frequency is before each use. Not daily, but before every single cycle. For biological indicators and steam sterilizers, the minimum requirement is weekly, but the recommended practice is daily. For ethylene oxide sterilization, the requirement is stricter. You must run a BI in every single load. If any load contains an implant, the requirement shifts to every single load regardless of the sterilization method. Interpretation of results. You must be able to interpret the results of a biological indicator test without hesitation. A test BI, which has been processed through the sterilizer, should read negative. This means no bacterial growth occurred. A control BI, which has not been processed, should read positive. This means bacteria grew, confirming the spores were viable. If your control BI reads negative, the test is invalid, and you must discard the lot. Recall logic. Regarding sterilization failures, remember the scope of a recall. If a biological indicator tests positive, you do not simply recall that specific load. You must recall all items processed since the last known negative biological indicator. This addresses the unknown window of failure between the last good test and the current bad test. Key terminology distinction. Finally, distinguish between validation and verification. Validation is the responsibility of the manufacturer. They perform the laboratory testing to prove the device can be sterilized. Verification is the responsibility of the facility. You perform the testing to prove the equipment works in your specific hospital environment. Golden Rule. We end with the golden rule that started this chapter. If it is not documented, it did not happen. Your signature or initials on a printout or logbook are your legal bond. Without that record, there is no proof of sterility, and patient safety is compromised.